Alright class, today we're going to talk about the cross product and what it's good for and properties and things like that. So it's kind of hard to see, but I'm claiming I have two vectors and I made them column vectors. I may switch back and forth between columns and rows. So this is vector u is ABC and vector v is DEF, and we define u cross v to be the determinant of this matrix with I, J, and K in it, and we put the row of u components and then the row of v components. Alright, and let me go one more step with this. So this would be, okay, so I'm writing it this way so we can sort of see what the goal is going to end up being. So BCEF, and then minus the J, and then ACDF, and then plus the K, and that would be ABDE. Okay, and so the reason to sort of think about it like this is you're going to end up with a vector something I plus something J plus something K, and these determinants determine what that's going to be, with the exception of this determinant is going to be the opposite. So you're going to minus whatever you get from that determinant. Alright, so let's do an example of that first, and with our example we'll also investigate some of the properties that we're going to see here. So we're going to let u equal the vector 2, 1, minus 3. We're going to let v be the vector minus 1, 1, 4. Okay, so u crossed with v, that's going to be I, J, K. Okay, let me copy these components down. So we're going to have 2, 1, minus 3, and minus 1, 1, 4. Okay, and then we'll break out under our minors. So we've got I times 1, negative 3, 1, 4, minus J, and then 2, negative 3, negative 1, 4. Plus K, and 2, 1, negative 1, 1. Okay, so here's what I'm saying. So I'm going to write this as a row vector, but we can change it later if we want. So the I component is going to be 4 minus minus, so plus 3. So that's going to be 7. The J component is going to be 8, and then minus minus minus, so minus 5. Sorry, minus 3. So that's going to be 5, but remember it's minus J, so this is negative 5 here. Okay, and the last one's pretty easy. That's 2 plus 1, so that's 3. Alright, so this is what u cross v is. And just note that we can actually investigate one of the properties just with this example. So what would u dot u cross v be? Alright, so this would be the vector 2, 1, minus 3 dotted with a vector 7, minus 5, 3. Okay, so that's going to be 14 minus 5 minus 9, and that's 0. Interesting. If we do v dotted with u cross v, okay, what's that going to be? Same sort of thing. Here, run out of room here. So minus 1, 1, 4 dotted with 7, minus 5, 3. And what's that going to be? That's going to be negative 7 minus 5 plus 12, and that is 0. Alright, so you remember from before, from a previous lesson, we knew that if the dot product is 0, the vectors are perpendicular. So that's something significant. So let's list down some properties that we might want to know. First off, we talked before when we were doing matrices, we talked about if you switch any two rows of a determinant, if you switch any two rows of a determinant up here, that's going to basically change the sign of the determinant. So that means, number one, that u cross v is not v cross u, it's minus v cross u. Okay, and there's a name for a property like that. So when you have something that does that, that's called anti-commutative. And not that you need to know that, but the key thing here, since they're just opposite signs, their magnitudes would be the same. So a lot of the properties, or a lot of the things that we would use this for, the cross product, we would maybe take the magnitude, and we wouldn't have to worry about which one we did. Okay, as we just saw, u cross v is perpendicular to both u and v. Okay, so that's significant. We get something perpendicular to both of the vectors. And then we have the distributive property, so u crossed with v plus w. So that's going to be u cross v plus u cross w. So the distributive property works like we would think. And then number 4, if I involve scalar multiplication, and I can move the scalar wherever I feel like. So alpha u crossed with v, that's alpha u cross v, whole thing, like that. Or I can even write it as u crossed with alpha v. So I can move that scalar around anywhere I feel like it. Okay, so just like the dot product, this one has a lovely trig relationship. So I'll say that we need to know that the sine of theta, which theta is the angle between two vectors, so I'm thinking of a picture that looks like this, like before. Okay, so sine of theta is u, the magnitude of u cross v. Once again, it doesn't matter which one I do first because of that magnitude, over the magnitude of u times the magnitude of v. Okay, so this is not good for finding the angle between two vectors, but it is good for doing things where you need to know that. So specifically, let me get a new sheet of paper here. So specifically, when would you want to do that? Well, so just like we did for dot product, we could actually have a theorem. Here, I'll even say it as a theorem. U is parallel to V if and only if U cross V is the zero vector. Okay, so I'm not going to prove this. It would involve the sine formula and all that good stuff. But the reason I'm not going to prove it is it's completely unnecessary, because we already know that if U is parallel to V, then U is a scalar multiple of V, and that's a much easier way to figure out if two vectors are parallel. Okay, but that is a thing. So if you do end up getting 0, if somehow you know these vectors are parallel, you should get 0 with the cross product. What else can we do? So let's say we have 3 points in 3 space. Okay, so I've got my points A, B, and C, and they make up a triangle. And this is actually really good to know for those of you guys that like math contests. So here's one of the easiest formulas to use when they give you 3 points. So the deal here is we've got the 3 points. We want to know what the area of the triangle is. So first of all, what we're going to derive, we're going to get something with the cross product, but we're going to derive that from the picture over here. So if this is my angle A and sides of length A, B, and C, if I want to know the area of that triangle, then the area of the triangle is 1/2 BC sine A. It is one of the best formulas for the area of a triangle. Much better than 1/2 base times height. All right, so how would we use that? So I'm coming back over here. So I need lengths and things like that. So what we're going to do is we're going to make a vector here and make a vector here. And the lengths of these vectors would be what I use in this formula over here. Okay, so the area of my triangle would be 1/2, okay, the length of AB times the length of AC times sine of the angle between. So we put my angle theta there. and then sine of that angle theta. Or you could say sine of A if you want. And so now we have the formula that we have for sine of the angle between two vectors. So the area of the triangle becomes 1/2. Okay, it looks really ugly at first, and then everything cancels off, so just bear with me. 1/2 the magnitude of AB times the magnitude of AC times the magnitude of AB cross AC over the magnitude of AB times the magnitude of AC. All right, and then we notice we have our cancel party, so the ACs and the ABs cancel. So the area of the triangle is merely 1/2 times the magnitude of the cross product of basically any two sides, if you vectorize them. That can come in very handy, okay? And then one other formula I'll give to you. So it's not just triangles, but we also have parallelograms. So also, if we had this parallelogram that looked like this, and we knew the coordinates of A, B, C, and D. So if that were the case, if we wanted to find the area of the parallelogram, that would just be, so if you think about it, that's two triangles and they're congruent. So that would be AB, magnitude of AB crossed with AD, and I wouldn't have need to take a half because there's two of them. And there we go.